can you, let's see. So is that still visible?
Yep, looks good.
Okay, great. Sorry for the snafu there. Okay, so yes, I am Francois Hebert. I'm a postdoc at Caltech. And I'll be sharing some updates on the development of the SpECTRE code, and in particular focusing on our work towards simulations of binary black holes. This is work done with many folks in the Simulating Extreme Spacetimes collaboration. So to provide some context here, I'll first start by reviewing the role of these simulations of binary mergers in astrophysics. I'll review some of the current methods used in codes today and the challenges that these codes face, which will lead into how we hope to improve on these methods, both in terms of the algorithms and the scalability in our new code SpECTRE, and then I'll show some results. A main motivation for these simulations is, of course, the discovery recently of gravitational waves. So LIGO and Virgo are gravitational wave observatories, and they've measured signals from merging binary black holes many galaxies away. And in order to process their data, they rely on accurate waveform models that are produced by computer simulations. So this enables them not just to characterize a signal that they see, in other words, say, oh, this looks like it came from two black holes that were this massive and were spinning at this rate, but it also allows them to look inside the data stream for weak signals. So on the left here is a visualization of the LIGO data where you can see how much power is in at different frequencies as a function of time. And there's a very loud signal here that you can see by eye, but sometimes the signals are much fainter and you need to do matching techniques to find correlations between the data stream and a predicted signal that you have in hand. So we give them these predicted signals. But looking to the future, these detectors will become much more accurate, especially space-based detectors on sort of decade timescales. And as these become more accurate, with less noise, we will need our waveforms to also become much more accurate so that we don't contribute systematics in the analysis pipelines. For the matter case, we've also got some really good results coming in recently with observations of merging pairs of neutron stars. The telescope recently actually directly imaging an accretion flow around a supermassive black hole. The simulations here are our best tool for getting a model for the matter dynamics. So what is really happening as the matter flows around. It lets us understand how heavy elements are created in these extreme environments, where heavy here in the context of astrophysics is really everything beyond helium. So everything we're used to interacting with in our daily lives, it's still not completely clear how and where it's formed. These simulations also give us a great tool for understanding the radiation that comes out from a merger event and relating it to observations of infrared, visible, ultraviolet, etc. Unfortunately, these hydrodynamic simulations in particular are very expensive, and we struggle to reach the accuracies that we're interested in. So let me give you a little bit of a feeling for what these simulations actually are doing. Here is a very nice visualization of a binary black hole simulation. So you can see a big heavy black hole in the center and a smaller black hole that is orbiting it. The black hole, the small one, is spiraling in as it loses energy to gravitational waves. And these color contours are a visualization of the curvature of the space-time that is carrying the gravitational waves out to infinity, where we might see them. So the thing to note here is that the space and time itself are the thing that's dynamical and being evolved. The black holes themselves aren't an object in the space-time, they're just a mathematical feature of the curved space-time. So we're evolving the space-time. And in the cases where we have matter, we still have to do all of that work of evolving the space-time. But on top of that, we now have very dense nuclear density matter, for example, in the case of a neutron star merger, that is flowing around, gets disrupted, it collides with itself, creating shocks, heating, turbulence, and all kinds of very complex dynamics. So to formalize a little bit what I've shown here in nice pictures, we're looking here to solve a large number of coupled PDEs. There's 50 of these for the space-time dynamics, and on top of that, there's a whole bunch for the GRMHD. The general form of these hyperbolic equations is given here. We have some vector of fields U that we're evolving, so this would be the 50 to 60 PDEs. And the time derivatives are given by some flux terms for equations that can be written in conservative form, or some non-conservative products relating to derivatives of U and sources. The complication here is not just the number of PDEs, but also the fact that they have some annoying features. So Einstein's equations that describe the evolution of the spacetime, for example, you have to worry that because the space itself is what you're solving for, you have to make sure you have a good set of coordinates that is a good representation of the features of the curved spacetime that you're interested in resolving. And you need to worry as well, of course, about the singularities inside the black holes. The methods that we use typically don't like infinities, and so we want to make sure we have a strategy for handling those when they come up. And for the relativistic hydrodynamics, you've got turbulence and shocks, as with any other hydrodynamic situation, but you also have to worry about your neutrino and radiation transport, nuclear reactions, and any other physics you may want to add in. So all of this put together is what makes this a challenging problem and why these simulations are long. The majority of codes that are in use today employ finite volume or finite difference methods to solve these PDEs. So I'll just sort of summarize a few key points here. We represent the solution as values at grid points. And typically the grids used are Cartesian grids, probably overlapping. If you're doing mesh refinement, you would overlap grids of different resolutions. A main reason that these methods are favored is that they have a robust collection of schemes that have been developed for handling shocks or other sharp features in the solution, like the surface of a star. So they're well suited to the hydrodynamics in that sense. The accuracy is what we call polynomial. In other words, the error between your numerical solution and the true solution decreases polynomially as you increase resolution. And here on the right, I'm showing some, not just the grid structure itself, but also this idea that once I partition up my grid onto multiple processors, and I need to make sure that the simulation remains causally connected across the domain, I need to send information to the neighboring grid patches. And I need to fill in this sort of little buffer region all around my grid patch, which is called the ghost zone. And unfortunately, this ghost zone has some depth to it, which means that I can't arbitrarily reduce the size of my grid patch because the volume of the communication is sort of unfavorable to that scaling. So these methods are used in the majority of binary black hole simulations today, as well as all of the matter simulations. Another class of methods that is used is what we call spectral methods. So here we represent the solution as an expansion over a basis. On the right, I'm showing an example, a very simple case. The grid patch is a square, and I'm going to use as a basis probably a tensor product of Lagrange polynomials or something like this. And we can often map these shapes to take advantage of any symmetries in the solution. One side effect of this basis expansion is that we really want to be using these methods for smooth problems. Otherwise, the basis will not provide a very good representation of the data. But when the problem is smooth, you get an exponential convergence. So the errors decrease very, very fast as you add grid points, which gives us really good accuracy and efficiency. To talk to the neighbors in this scenario, you're only sending boundary data. So the orange points at the edge of my little figure here show the data that gets sent out to the neighbors in each corresponding direction. So this is you let your neighbor know what the flux is through your interface, and then you can apply corrections to connect the domains together for the simulation. So these methods are the state of the art for binary black hole simulations, giving the best accuracy and the fastest simulations. To run these simulations on big computers, most codes today use message passing, MPI, with some threading. Typically, a finite volume or difference code will scale to ballpark 10,000 cores. I'm going to say a little bit more about SpEC, which is the code of our collaboration that we use the spectral methods in for doing simulations of black holes and spacetimes with matter as well. So here we distribute one spectral element onto each core. And if we're also doing hydrodynamics, we have ballpark 100,000 cells per core. But our code really scales only up to about 50 cores. And part of this is the number of spectral elements and is really a reflection. This statement applies to the finite volume as well. These scaling limits are really a reflection more of design choices that were made some number of years ago, maybe 10, 15 years ago, before we really had to worry about exascale computing, rather than fundamental limitations about the PDE solving methods. So I've opened by saying that we would really like our codes to be producing more accurate simulations, but unfortunately, we're already sort of at the limit of how patient we can be. So simulations of binary black holes will take maybe a week to multiple weeks for hard parts of the parameter space, if one black hole is big and the other is very small, or if you need many, many orbits. Simulations of binary neutron star mergers will take a month to multiple months. And so to get the improvements in accuracy that we're looking for, but not stretch the limits of our patience, we're really looking here to improve the not just the numerical methods to solve the PDEs, but also the parallelism algorithms to get better scaling. So this is our motivation for having started work on our next generation code, SpECTRE, for relativistic astrophysics in particular, but it's a PDE solver more broadly. We're going to improve the algorithms by using discontinuous Galerkin. So we've heard already a few statements, but I'll say a little bit more myself. And we're using, of course, task-based parallelism with Tron++ to enable more flexible workloads, really, because these astrophysics problems are not very homogeneous. And so one struggle that we have is making sure that the load is well distributed across the computer. So in the remainder of this talk, I will be showing a little bit the methods that we use for our binary black hole simulations. And I'll be giving some preliminary results for the binary black hole, as well as some load balancing experiments we've just started doing in Tron++. A big focus of SpECTRE has also been to think more carefully about the hydrodynamics algorithms. So this was actually just discussed in the Q&A of the prior talk, but that will not be in the scope of this talk today. Discontinuous Galerkin is a generalized spectral method for solving a PDE. So it has most of the features that we really liked about spectral methods. For example, it has the basis representation of the solution, which enables really good exponential convergence when your solution is smooth. It maintains the geometric flexibility. But on top of that, it sort of gives you a framework for thinking about how to fall back to shock capturing schemes where that may be needed. And this enables you to think of this method to handle both the space-time and the hydrodynamics together in the same scheme, sort of unlike what we've been doing in our codes in the past. As per spectral methods, the communications are typically nearest neighbor boundary data only. So this is a lightweight and efficient. And you can formulate AMR and local time stepping in here as well, which will really let us put the resolution, not just the spatial, but the temporal resolution as well, where it's most needed to get the accuracy we're looking for. So to show you that this all works, here's a simple code test of an evolution of a single black hole. So there's an exact solution for this space-time. So we can do our numerical simulation and compare it to this exact solution and check how well we're doing. So that's what is done in the plot on the left, which is showing the error in the space-time as a function of time. And you can see that as you go down through these curves and we're adding more and more grid points, the error drops by, in fact, more than an order of magnitude every time you add one grid point per dimension. So this is the exponential convergence I was just talking about. So this is a great result. And then on the right is a plot showing that this is stable. This is just one resolution, but now evolved for 100,000 dynamical times, and it's perfectly smooth. So the code is nice and stable for single black holes. We've also tested the convergence, sorry, the scaling. So this is a result from a couple years ago now on blue waters, where we're showing weak and strong scaling of SpECTRE. The green lines here are the strong scaling, where you divide the problem into more and more processors, and you hope that the runtime will linearly go down, and we find that it very nearly does. And the blue dashed lines are the weak scaling, where we solve a bigger problem on more processors, and we hope that the runtime stays constant, and again, it nearly does. So this is going up to about 100,000 cores. And so this makes us feel pretty good about our choice of Charm++ as scaling really well to large numbers of processors. Now, from here, I'm going to outline a few of the ingredients that are necessary to do a simulation of two merging black holes. The first is, of course, you need initial data to start your simulation from. And we can't just evaluate some function because we don't know what the space-time is at an arbitrary time. That's why we're doing the simulation in the first place. So typically we'll take an initial guess, perhaps the space-time of two black holes, and we just sort of put them next to each other and superpose that space-time. And then because that's not a valid solution that satisfies the constraints of Einstein's equations, we have to solve some elliptic constraint equations to make that be a valid initial solution. So we have a code and development within SpECTRE to do this, but we can actually, for now, just read in initial data written out by our prior code, spec, and start from that. So that's what we'll be doing here. I've discussed the solving of the PDEs using discontinuous Galerkin, and we couple that with a time stepper to actually do the time integration. So for example, something like Rangakata. And then I had alluded previously to this issue that you need to make sure you don't have the singularities on your grid. So let's say a little bit more about that now. We use a technique called excision, in which you really just cut out the interiors of the black holes from the simulation domain. You probably know that nothing escapes a black hole, and this applies in the simulation as well. So we can cut this region out, and no data was coming out from within that region, so the causality of the simulation is perfectly fine. So the upper panel here is showing what the computational grid looks like in the coordinates in which we're solving the problem. And so you can see these two regions that have been cut out. The problem is that the black holes are orbiting, they're moving around each other. And so we need to constantly shift where these excised regions are so that they line up with where the singularities are to make sure we keep cutting out the singularity. So we're using the same kind of moving mesh prescription that was described in the previous talk. Well, not the Voronoi, but we're moving the mesh. And this requires a little bit of sophistication because as the black holes are orbiting in, they get closer, the orbit accelerates, and the black holes are going to get distorted by the tidal forces on each other. So we have a control system that measures the positions of the shapes of the black holes, updates these maps that rotate the grid, and then from the moving mesh, we add some corrections to the time derivatives. And so this lets the whole thing hang together. This as well is currently in development in SpECTRE. But SpEC uses the exact same approach to handling the singularities by rotating and adjusting the grid. And we can read the moving mesh data from a SpEC simulation of two black holes with the same parameters into SpECTRE, and then just use that. So I'm going to show now a movie of our sort of initial attempt at a binary black hole evolution in SpECTRE. This is a cut through the equatorial plane, which is colored by the lapse. The lapse is one of the space-time curvature components associated with the rate of flow of time. So what you're seeing here in yellow is the idea that time flows closer if you're closer to the black hole. And I'll just play it now, and you'll see that the black holes go round and round, and the manually excised regions that we're imposing in SpECTRE are exactly being matched by the dynamics of the black holes, which is a really good confirmation that SpECTRE is doing the same evolution that our prior code spec was doing. So now I want to switch gears a little bit and talk about how we're using Tran++, and then a little bit of exploration into load balancing. The different components of a SpECTRE computation map nicely onto the chars of Tran++. So the elements are represented by a char array, and they're responsible for storing the solution on that little patch of the grid and computing time derivatives, doing time stepping, and sort of really managing the data. And then when we need to do other tasks, typically we will send data to some other chars where they will, for instance, do some data processing. Maybe it's for I/O to make a movie, or we need to interpolate the data to get it on different sets of grid points. We will do this typically on groups and node groups. And then single computations like measuring the position of a particular black hole or computing a gravitational wave as it would be extrapolated all the way to infinity, these we do on singletons. So the elements or the array chars are constantly talking to each other in this nearest neighbor communication pattern to keep the simulation in sync and exchange neighbor information. And then we've got these sort of sends out to other more special chars. So the PDE structure here is imposing causality, which forces the entire evolution to remain roughly synchronized. But for this to be efficient and to not have any idle processors, we really would like to make sure that the load is uniformly balanced across the simulation. And this is going to become much more important in the near future when we start thinking about AMR, local time stepping, and things that could really cause certain particular regions of the simulation to be much more computationally expensive. So we're approaching load balancing here with a couple of sort of naive questions because it's our first go at it. For example, if I have a bad distribution of chars onto nodes, can the load balancer improve it? So to clarify what I mean, say I have a char and all of my neighbors live on a different node of the supercomputer. Every communication I have to do to exchange fluxes and do the time integration of my PDE is going to be a slow communication because it has to go through the network. However, if I have a very good distribution where all of my neighbors are on the same node, so we can have very efficient communication channels. So this might be a good distribution as obtained by a space filling curve. And then I use a load balancer. Will the load balancer preserve my good distribution? And of course, we'll also be thinking about load balancing in the context of inhomogeneous loads in the future. We've got a pretty straightforward implementation. This is sort of our first pass at this, where we've added global synchronizations every n time steps into the code. We call at sync, then we resume time stepping after the load balancer is done. The subtlety here was our array elements have to register with the groups that they send data to, for example, for I/O, because the group needs to know when it's done waiting for data and when it can write the file, for example. And so when we do migrations to load balance and the array is moved off of that processor, we need to make sure the group knows not to keep waiting for data. So we need to add some deregistrations and re-registrations as you move, as you migrate array elements from processor to processor. Here is a very small test showing one way that we were looking at the load balancing results as a function of sort of the initial distribution of processors, of the array chars onto processors. So on the left of this plot, every communication goes to a different node. So every communication is slow. And on the right side of this plot, every communication, or the majority of them, are local. And only very rarely do you have to talk to a different node, which is slow. And you can see that when I use the dummy load balancer, there's a huge spread in the runtimes, a factor of 7 actually, where the case where you've got good locality of the chars is significantly more faster. So what this tells us, communications really are an expensive operation in our code. And then I've also picked out a couple of other load balancers just to show that these are the communication aware ones, and they clearly are converging each of them to some state. where independently of what I gave as my initial distribution, they seem to converge to something. And the one here that's most interesting is this recursive bipartition algorithm that is all the way at the bottom, and which gets to within about 20% of the performance of the manually tuned case. So this is pretty encouraging, especially faced with this sort of huge spread of possible runtimes. But that last 20% may also be worth chasing with something like a space filling curve or a load balancer. But this is really a tiny problem with 1,000 array elements on 2 nodes. We're trying to understand now what happens if we scale up, and we're seeing some slowdowns that we don't yet quite understand. So the curves here are showing the recursive bipartition load balancer as I go from 2 to 4 to 8 nodes, and it takes more time to do a time step. And we're not quite clear at this point if this is just the expected increase in the computational cost of the load balancer as a result of scaling up the problem. So the graph it's trying to partition is larger. It's not quite clear on the run this short, so we're going to have to test longer runs, whether this might be an issue with the load balancer actually slowing down versus time after repeated upload, whether this might be a performance issue in SpECTRE that we aren't aware of yet. So we need to benchmark that as well. We've also been looking at checkpoint restarting. From the global synchronization point we had to add for the load balancer implementation, it was quite straightforward to add a start checkpoint function. And the data here on the right shows that in this first example, the restart works perfectly. So the orange curve that starts at time of 3, it just picks up from a checkpoint that was written and has the same evolution as the full run that it's starting from, with deviations varying only at the level of round off, which is actually not unexpected for SpECTRE because some of our operations depend on the order in which term++ messages are received. And so we can't guarantee the bitwise reproducibility. We have to generalize this to work on, for example, restarting on a different number of nodes and other things like this. So going through this, we've come up with maybe I'll call this a wish list of things that would have been good to know while we were thinking about load balancing and checkpoint restarting, things in particular related to documentation and how it's not always clear which load balancer should be used, or how a load balancer makes its decisions, or how it would scale as you increase the complexity of the problem, as well as some thoughts on the initialization sequence for a checkpoint restart. That last 20% in speed between the recursive bipartition and the manually tuned case is also interesting and makes me wonder whether a load balancer based on a space filling curve might be worth pursuing, though it might need to be made aware of, for example, the connectivity of the domain of the simulation that you're using. And then finally, our checkpointing is writing a number of items to the disk that are really not necessary because they're temporary caches. So a context-aware pupper would actually be quite useful here. So these are just some things to think about. Can come back to this after, but for now I'll summarize. So I've described some of the reasons that we're interested in these simulations of binary mergers. I've said a little bit about what the struggles are for current codes and how we hope to improve on this with SpECTRE. And then I've shown some preliminary results from a binary black hole evolution and our first sort of stab at term++ load balancing. Thank you.
Thanks, Francois. We do have one question from the Google Doc, and that is, what exactly do you mean by rec by part plus dummy? Does that mean you're alternating those balances?
Yeah, good question. So we're using here the feature where you can specify 2 load balancers on the command line, where it would apply the first one, the first invocation, and then it would switch to the second one thereafter. So what this means here is that the first time the load balancer was applied on the left side of the plot, it's using the recursive bipartition. And after that, it's the dummy load balancer. And so this plot here, the comparison between the green and the red curve, so the one at the top and one of these at the bottom, is the difference between applying recursive bipartition many times or applying it just once.
Okay, yeah. Do we have any other questions for Francois? I don't see any others in the chat or the Google Doc.
I had a follow-up just from that. So I was going to ask the question originally, but one thing I was also wondering is if you've done anything with graph partitioning load balancers, because you're saying that communication time is really important.
So here, one of these curves is the graph by partitioning, I think. Is that what you're asking?
No.
That's what I'm asking, but I don't think any of these really does that.
What's graph BFT? I don't recognize that.
It's one of the ones that was suggested to me when I typed plus balance or help, and it sounded promising, so I used it. So yeah, so it's.
Ranak, do you know?
I don't know off the top of my head. It's one that I think is rarely used, so it hasn't been around in a while. But I can look at it. It might do something similar, but the ones I'm talking about are more in the vein of what Metis does.
Oh, we've tried using the Metis ones, and we have found some reproducible, but that we can't understand error messages and seg faults. So we're not quite sure what's going on with the Metis load balancers, but we would definitely be interested in trying to work out what's going on.
Okay, yeah, that's something we'll follow up on with you guys on later.
Yeah, great. Yeah, I mean, any insight into how to best choose and use load balancers would be very helpful, because the initial experiments make it not always clear what the best strategy is.
This seems like an excellent use case for us to use for the load balancing research, and just even to test various things. Is that something that can be made available to us?
The code that we have here?
Yeah, I mean, configuration code, whatever. So we know exactly we can test different load balancing strategies.
Yeah, probably. I mean,
yeah, I mean, that's all on a public fork,
there's-
and to be honest, I don't see why we
Yeah.
probably can also get you accounts on the exact systems, HPC systems that we're running, because they're ones we own.
Okay. In addition to what Ronak mentioned, there is a strategy that Kavita had implemented called Graph Refine that can preserve, like it migrates only among near neighbors. So I want to look. I want to see what the status of that is, and we'll get back to you.
Oh, that sounds potentially very useful. Yes.
Yeah.
Do we have any other questions for Francois?
So I had just a naive load balance question. So the rec bipart, or is that one of the default, or sorry, is that available in the charm distribution, or did you write that yourself?
Yeah, sorry. I should have said this. All of these are from the Charm++ distribution.
Okay, thank you.
Some of these are compiled not by default, but by adding a different flag. So I don't remember which is which. The recursive bipartition might be one of the fancier ones that you have to enable by compiling every LB or something like this.